Number 4, trying to find the relative minimums and maximums of f of x equals negative cosecant of 2x on the interval from 0 to pi over 2. So you'll notice the trig ones, a lot of times you'll have an interval to look at because they're periodic and they kind of repeat themselves, so a lot of times they have infinitely many minimums and maximums. So let's go ahead and figure out our critical values first by finding the derivative. What's the derivative of cosecant? Negative cosecant cotangent. So with a negative out in front of there, times that negative, we're going to end up with cosecant of 2x times cotangent of 2x. And then we have to multiply by the derivative of the inside. We're using chain rule here. Derivative of 2x is just 2, so I'm going to put that out in front. And we want to know when is this equal to 0. So we can set each one of these factors equal to 0. Either cosecant of 2x equals 0, or cotangent of 2x equals 0. So cosecant 2 can't equal 0, so we don't even bother with it. If you want to put it here, you could put it there. No, because when you divide by 2, what do you get? 0. Right. So for this one, cosecant of 2x equals 0, that would mean that 1 over sine of 2x would equal 0. Right, so a couple things here. One, we have something in the denominator, so if that's equal to 0, that's going to make this derivative undefined. So we should set the denominator equal to 0 also. But if we look back at our equation, our original function is cosecant of 2x, which would mean like 1 over sine of 2x. Whatever makes this denominator 0 would also make this denominator 0, meaning that it's not part of the domain. It's not in the function. So there's no point in setting this denominator equal to 0 in this case. Kind of like quotient rule, when I told you don't even have to bother setting that denominator equal to 0 because it's going to make the original function undefined and it's not part of the domain. So if we go on to solve this, we're going to multiply both sides by sine of 2x. Over here that cancels out, but over here we just get 0, so we get 1 equals 0, which is not going to give us any solutions. So this doesn't help us at all. No critical values from that. Over here, we get cosine of 2x over sine of 2x, that's the same as cotangent, would have to be 0. So again, we know sine of 2x can't equal 0 because that would make the original function undefined. So we want to figure out what makes cosine of 2x equal to 0. So on the unit circle, when is the cosine equal to 0? Pi over 2 and 3 pi over 2. Right? So 2x would have to equal pi over 2 plus pi n. Right? That would account for all the possibilities. Although we're looking at an interval, we want to kind of take a look at all the possibilities first and then narrow it down. So to solve for x, we can multiply both sides by 1/2. That means x is going to be pi over 4 plus pi over 2n. So now we want to look at that interval. Our answer has to be between 0 and pi over 2. So pi over 4 is obviously in between those. But after that, everything else is going to be outside of that interval. So on our number line, we only have one critical value in that interval. That's pi over 4. So we just need to check to the left and to the right. So we can use pi over 6 and pi over 3. It has to be in this interval between 0 and pi over 2. Remember, we just need to know, is it positive or negative? We don't have to figure out the exact value. So if we look at our derivative here, if we put pi over 6 in, we get 2 cosecant of pi over 3, because the 2 times pi over 6 gives us pi over 3. So cosecant of pi over 3, well, that's the reciprocal of sine of pi over 3. And again, all we need to know is it positive or negative. So is sine of pi over 3 positive or negative? Positive. Okay, and then cotangent of 2 pi over 3, which would be cosine over sine of pi over 3. That's going to be positive also. So this is going to be positive. If we try pi over 3, we get 2 cosecant of 2 pi over 3. So sine of 2 pi over 3 is positive, so that means cosecant of 2 pi over 3 is positive also. So that stays positive. And then cotangent of 2 pi over 3, cosine over sine. Well, cosine is going to be negative over there. Sine is still positive, which makes the cotangent negative. So our derivative is changing from positive to negative when x is pi over 4, so that means the original function f has a local maximum at x equals pi over 4.